C dividers for DC voltage measurement. First question I often get is, what is a fiber optic CT? An optical CT uses Faraday effect to measure the magnetic field produced as the current flows through the CT head. Basically, the light comes up, passes through the CT head, and Faraday effect causes a change in the angle of polarization of the light as it passes through the head. It hits a mirror, returns, goes back to the electronics where the signal processing occurs. The signal processing produces a digital value that corresponds to the current that flows through the bus as it passes through the head. From there, we can output the digital measurement over process bus using 61850 protocol, or we can convert it back to a current or a voltage for use with conventional IEDs. Where do we use optical CTs? Well, quite often they're using them in scenarios where they have to make a measurement that can't be done with conventional instrument transformers. One example here in North America was with nuclear operators. Nuclear operators had an issue with their auxiliary power transformers where they were unable to detect an open phase condition if they lost a conductor coming into the power transformer. There are a lot of solutions out there, but our solution was simply to measure the current going into the transformer when the transformer was unloaded. There's a small amount of magnetization current flowing in and out of the transformer as the voltage rises and drops. That current could be on the range of 10 to 50 milliamps, which can't be measured with conventional CTs. The fiber optic CTs can directly measure that current, and we use bicon relays to trip on a low current setting. Another example was in Europe with cable fault detection. In Europe, utilities are undergrounding a lot of their cables. And in order to provide a blocking signal for the underground portion of the cable, they either need to build a substation at the cable transitions, or they either just block reclosing on the transmission line altogether. Using the optical CTs, we can install just the CTs at the cable transitions and bring the signal back over optical ground wire to the substation. From there, we put it into a differential relay, and the differential relay can provide the blocking signal to the reclosing relay. Obviously, that saves the utility the cost of building a substation at the cable transition compound. We can also mount the CTs horizontally, so in many cases, the utility simply installs the CT horizontally on the transition structure and passes the cable through the CT, not requiring any additional civil works. Another example in Australia is geomagnetic induced currents. They have a large problem with geomagnetic induced currents from solar flares in Australia. And traditionally, utilities have addressed this by looking at the neutrals on their power transformers. They install low-cost DC current measurement devices on the neutrals and look for how much DC current is flowing from the power transformer to ground at the power transformer. That doesn't tell the whole story of how the GICs are flowing through the network. So some utilities are starting to install optical CTs on either the high side or the low side of the power transformers and measuring the slow varying GIC currents using the optical CT and using that to model the system behavior and determining how the GICs are flowing through their network. For more information on these applications and on other products within the DIT portfolio, please visit our website.